So hopefully by now you feel pretty comfortable with the basics of integration. You've done a lot of integrals, you've used the direct method techniques, for instance, if it was x dx, you would just add 1 to the power and divide by that new power. Of course, adding c. There's, any number of other ones, e to the x, or maybe like natural log of x over x, or just 1 over x. There's a lot of integrals that you've learned, and there's a lot of the, sort of like those tables of integrals, that so you can match something to the form. But the problem is that even though the integral that you may be looking at has the ability to be solved by direct substitution or by direct integration or by u substitution, that doesn't mean that you're going to be able to easily see that. What you might have to do is some additional manipulation. So what I want to talk to you about today are 7 techniques that can be used, or manipulation methods that can be used in addition to those standard techniques, that may help you avoid having to use more difficult techniques, or it may save you a lot of heartache altogether. Because at its heart, solving integrals is really more of an algebraic exercise. The goal is to get it to something that has been solved before and then use that. So we have to find ways to fit that. So let's go through some examples. And again, I've got 7 here. The first one is something called expansion. So if I'm trying to integrate 1 plus e to the x squared, quantity squared, dx, then what I want to do here is I simply just want to multiply everything out. And in general, that's a great method if you can use it. So by doing the FOIL method, or however you want to distribute this, you get 1 plus 2e to the x plus e to the 2x. So this is obviously directly integrable, goes to x. This 2e to the x just integrates to 2e to the x, that's direct. E to the 2x requires a u substitution unless you understand the table method, but again, by just expanding that, you get something simple here. The next one is one that I find students have a lot of trouble with, but is a very powerful technique and comes up a lot. And it's the idea of separating the numerator. So what you want to do if you have this, or one thing to try, because again, you don't always know the technique, but you at least try one. If it doesn't work, kind of move along. So for separation of numerator, what you do is you say, all right, can I separate every term in this numerator into a distinct fraction? And then by having them in distinct fractions, are those integrable? So if I take 1 plus x over x squared plus 1, I can separate that into 1 over x squared plus 1, and that uses one of those trig integrals. I believe it's arctangent. And then this goes to x plus x squared over 1. So I take each piece of the numerator and put it over the same denominator, separated into fractions. This is a simple u sub. You take u equal to x squared plus 1. du will be 2x dx, so you just need to have a 2 there. Or you can divide by 2. So the idea is, just by separating it up, you now have something that fits those tables. The third one is, in my mind, doesn't have to be complicated, but I find that students have a lot of trouble with completing the square. So completing the square is a technique that's technically a pre-calculus or maybe even earlier technique, but I find that students do not do often enough, and so they don't feel comfortable using that. So in the case of completing the square, we have 1 over 2x, or the square root of 2x minus x squared. And what we find is we can convert this to that. However, since students are so poor, I'm going to go ahead and do that for you right now. So I'm going to take this blue marker here, and I'm going to say, okay, how do I get from here to here? Well, when we complete the square, what we want to do is we want to write this thing in descending order. So I'm not going to use the square root for a moment. I'm going to say, all right, negative x squared plus 2x. Then what you do is you factor out the leading term. You pull that all the way out, so you have negative x squared minus 2x. Now what you do, so if this had been like a 3, you'd want to pull a negative 3 out of everything. So that would have pulled a 3 out of this too, and you would have had like a 2/3, which is less fun, but this method I think works better than some of the other ways it's taught. Along that same line, what you do here is you take this term now. You take this coefficient, this negative 2, you cut it in half and square it. So you cut it in half, that gives you negative 1. Squaring it gives you positive 1. So what we're going to do is, again, we keep that here. We get a positive 1. However, we don't just get a positive 1 for free. We can't just conjure it from nothing. So we really have to sort of add a 0. So what we're doing is we're conveniently manipulating this so that we can pick things apart. So we're adding a 1, but we have to subtract a 1. But all I want are these first 3 terms. So what I have to do is break this out of the parentheses. So when I distribute the negative to this negative 1, what I get is a negative x squared minus 2x plus 1. And then I get a positive 1 out here. Now I have something that is what's called a perfect square. It can be factored. If you factor it, both factors are going to be identical. In this case, those factors are x minus 1 and x minus 1. So you end up with a negative x minus 1 squared plus 1, which is identical to the way this is written. But even in this particular case, if you had been given this integral, or this integrand, the integrand is the thing that you're integrating, is that term, the function. If you're given this integrand, you could write it like this, but you're still not done. You would have to use a u substitution of u equals x minus 1, and then you would have something like 1 over 1 minus u squared, or square root of 1 minus u squared. Now, then that integral is like an arc sine. So you could it now fits the form of an arc sine function. So there's a lot of work that has to be done here, but these manipulation methods allow that to be possible. Let's keep on rolling. Now we're getting into ones that I think are a little more complicated for students. First one being rational division. I don't think students like rational division at all. So rational division is this idea of doing long division or somehow dividing the polynomials. And I don't really have room here, and it technically isn't a calculus skill, so I don't want to go too far into it. I wanted to do completing the square because it comes up, but rational division, But I strongly urge you to check this out, because what you can do is by dividing this polynomial into that polynomial, what you get is 1 minus that. You sort of get a remainder. In this case, that remainder turns out to be negative. 1 minus 1 over x squared plus 1. So this directly integrates to x, and then that is that arctangent form. And that's pretty complicated. I will say this much. I tend to avoid rational division. I tend to favor the method 5, and that's this idea of addition or subtraction in the numerator. So what that allows you to do is it allows you to look at the bottom and the top and go, okay, how could I conveniently factor or conveniently manipulate this to avoid having to do that? So in this case, I have x squared plus 2x plus 1. And so what I might want to do is, if I were integrating this integrand, I would say I want u to be my denominator. So if I take du here, it's going to be 2x plus 2. Well, the problem is I don't have 2x plus 2, I just have 2x. So what I can do is I can conveniently say, okay, well, I don't have 2x plus 2, so if I make 2x plus 2, I can't just pull 2 out of a hat. I have to subtract. If I add it, I have to subtract it. The balance has to remain. So then what I can do is I can use that technique, and then I can apply this technique. I can say, okay, well, I'm going to conveniently separate this over here, and then that negative 2 is over this one. And you might say, well, that's not very helpful because u was this. Well, in this particular case, now you're going to have a separate u. The u substitution for this one is going to be x squared plus 2x plus 1. And then over here, you're going to have another substitution, maybe not u, maybe you should use t or something, of x plus 1 squared, or x plus 1. So by doing that, you'll get like 2 over t squared, which is, that's a power rule. And on this one, you'll have the u here and du there. So this will be absorbed, and you'll have 1 over u. So this is like a natural log, and this becomes like negative 2 over t. And then t is x plus 1, so, or positive 2 over t. So you can apply these techniques to manipulate them, to mold them towards the types of integrals you're looking for. Next up is trigonometric identities. There's a bunch of these, but the key is to selectively identify them. That's not very useful. We're going to learn some more trig techniques as we go on, so you're going to have to say, okay, is it this one or that one or this one? What you find in integrals is that it's just it's kind of a crapshoot. When you derive things, you typically just throw the differential operator on it, that ddx, and just run with it and just go. With integrals, you're going to be like, does this work? Not really. How about that? How about that? And so with this, for instance, if you started off with cotangent squared x dx, well, integral of cotangent squared is not very straightforward, but if we change that to cosecant squared x minus 1, then what you find is that's going to be, I believe, negative cotangent of x is the antiderivative, and then of course negative x is the antiderivative, and that comes out fairly cleanly. And finally, conjugate multiplication. This is actually one of my favorites because I love manipulating. To me, it combines the beauty of trigonometry and algebra, and I kind of geek out on it, but it's one of my favorites. So if you have the way to usually identify these, not always, but the way to usually identify these is that you have some sort of 1 plus trig function in a denominator, or 1 minus a trig function in a denominator. That's usually the way to identify these. And so what you do is, okay, well, I have a 1 plus, so I'm going to multiply top and bottom by 1 minus the trig function. Or if it was 1 minus in the bottom, I'd multiply top and bottom by 1 plus. So in doing that, I get 1 minus sine of x in the numerator, I get 1 plus sine of x and 1 minus sine of x in the denominator, and then I can use that difference of squares formula. A plus b times a minus b is a squared minus b squared. So 1 squared minus sine squared of x. But 1 minus sine squared of x has a trigonometric identity. That's cosine squared of x. So now I can separate that, or I can reduce that to cosine squared of x, which doesn't sound that useful, but then we can apply number 2. Notice that this thing keeps coming up. It's very, very common to use that. We can split that up into 1 over cosine squared of x and sine over cosine squared of x with that minus there. 1 over cosine is secant, so 1 over cosine squared is secant squared of x. And secant squared of x has an antiderivative of tangent. And then in this particular case, you'd actually have to use u substitution. You'd take u to be cosine, and then du would be negative sine of x. And then you'd end up with like 1 over u squared, which antiderives to negative 1 over u. So your answer ends up being like tangent of x minus secant of x plus c. Something like that. I know this was a lot, but we're going to do some examples. We're going to try to incorporate a lot of these into what we do, but these are kind of your basics. These are your fallbacks on how to manipulate these integrands to make them fit the tables better, because that's, at the end of the day, that's really what you want to do. You want to shove them into the tables so that you can pull out that antiderivative.